Test, test.
Hi, Jason. We can hear you.
Thanks. Test, test.
You have your screen up right now. We can see it.
Explain variance is high. Your data are rich and your model's good looking. So hush, statisticians, don't you cry. Your data are rich and your model's good looking. So hush, statisticians, don't you cry. So hush, statisticians, don't you cry.
All right, everyone. That was some more stats music from Michael Greenacre, just like the p-value song. I'll leave the link for that and some of his other work in the YouTube and on the Facebook post a little bit later. My name is Russell Gray, and this is the third day, or the third day of the Ecology and R web conference series. And today we're going to be focusing on spatial ecology. We had some technical difficulties the last day with live streaming and Facebook. Still haven't really sorted that out. So now we're transitioning from there over to YouTube. So if you're watching on YouTube and you have people on Facebook that don't know how to watch the live stream, please let them know and give them the link. We're gonna have our speakers talk first, and then you guys can ask your questions afterwards. We have a Q&A dialog box, so please ask there. And if they can see it, they'll answer you. If not, then I will read the questions out to them and they can answer as they go. Okay, so without further ado, I'll introduce our first speaker, Jason Airst from Nova Scotia, Canada. Go ahead, Jason.
Hi. Okay. Can everyone see my presentation?
Yep, all good.
Great. So, hi, my name is Jason Airst, and I work for Nova Scotia Lands and Forestry, which is with the Nova Scotia government. And today I'm going to be talking about using density surface models to improve the accuracy of distance sampling surveys. So Before I get started, I'd like to acknowledge that the work that I'm going to be going through today was collected in Unama'ki, the traditional enunciated territory of the Cape Breton and Mi'kmaq people, and that this work was done in partnership with the government of Nova Scotia, me, Parks Canada, as well as the Unama'ki Institute of Natural Resources and the Confederacy of Mainland Mi'kmaq. And the data I'm using comes from a 2020 aerial survey done on moose, where we covered an area of just under 7,000 kilometers squared. This area was divided into 5 subregions, which are each managed differently for moose. And we observed 121 groups with 314 animals. So what is distance sampling? So distance sampling is a survey technique in which you note the location of animals seen in relation to a sampling line or a sampling point. And then you use this information to create a measure of citability for the number of animals you have likely missed. Now, this model assumes that animals that are farther from the line are harder to see, and thereby that's why we see fewer animals farther from the line, and we have to correct for this to get a true abundance of a population of animals we're surveying. So the package that I'm first going to talk about is a package called distance. In this package, the function used to run this type of analysis is ds. In this, the data line represents the name of your data set, either in a single flat file or in separate region tables, sample tables, and observation tables. Transect tells the computer whether we're doing a line survey or a point survey. Truncation is used to create a right truncation, which means you are removing values that are farther away from the line because you think that the locations that are really far away from the line are overly influential or are, in fact, mistakes that were made. Cut point allows you to, instead of using a continuous distance range, to instead bin your distances into smaller groupings, such as, let's say, every 100 meters rather than continuously from 0 to 500 meters. Convert unit allows you to convert the distance measure to another unit. Oftentimes this is done because when you're collecting data, the length of the line you're going on or the area of the region you're looking at are all in kilometers or miles, while the distance away from the line is often calculated in measures such as meters and feet. So you either have to correct this before you do the analysis or use this function to correct so that everything is in the same unit as everything else. And formula allows you to put in effects into the model to see how they impact the citability curve. And finally, the key function is used to add a regression line to the detection curve. And your choices in this are a half normal, hazard, or unified detection line. So this is my flat file from my data. And you can see that the rows have kind of odd names. And this is because the program requires this naming convention to work. So sample labels represent the name of each of the lines that were flown. The effort is the length of these lines. The object number is the unique object number for each group that was observed. The size is the size of these groups. Distance is the distance that group was seen away from the sampling line. Region label is the subregion the samples or the lines took place in, and area is the area of that subregion. You can see that if you have more than one observation on the same line, the way you deal with this is having 2 rows with the exact same sample label, but having a different object label. And further, if you have a line that had no group seen on it, you enter that in with a blank row for object size and distance, but the row still is included. If you don't include rows that don't have observations, then your summary statistics are just going to give a detection curve. And if you don't include a size row, then the model will assume that all your groups have only one individual in them. Finally, if you don't include an area row, then your summary statistics are only going to give you a density measure, not an abundance measure. So this is what my data looks like when I ran it. I chose to use a half normal distribution with a 10% truncation, and this was chosen based on it producing the lowest AIC value and also the lowest coefficient of variance. And the summary statistics for this give you an estimate, which is the slope of your detection curve, a standard error, and a coefficient of variance. And when we plot that, we just use the plot function. We get a detection curve, and we see that, in fact, most of the observations do happen closest to the sampling location. And as we move farther away from our sampling location, we have fewer and fewer observations that have been made. So just to be clear, the observations all took place between 0 and 0.33 kilometers from the line, and that we removed 5 groups when we truncated the last 10% of the data. So in the other summary information you get out a summary of clusters, which represents the information about the groups. And if you included a size variable in your table, you'll also get a summary of individuals, which tells us the density and abundance of the population on the landscape. Now, the summary statistics up here are the area of the region we're looking at. The effort is the amount of flying that was done in that region. So we flew for a total of 180 or 1,800 kilometers. And the cover area is equal to the effort times twice the maximum distance out we were looking, because we're looking out 300 meters on either side of the helicopter. That works out to 1,800 times 0.66, which gives you roughly 1,200 kilometers squared. Now, the other part of this is that the density table tells us the density of this population after correcting for the abundance using the detection curve. And this is calculated based on this corrected count divided by the cover area. And the abundance tells us the abundance, which is the density times the total area covered. And in all cases, we're getting a standard error, a coefficient of variance, and a 95% confidence interval. And in the summary of individuals, we also get information about the average size of groups we're observing, which in my case was 2.2 moose per group. If you don't include the size information in the original table, then you're only going to get the summary of clusters, which does not include the average size of these clusters. Now, the distance sampling package gives you a lot of good information, but it doesn't really tell us how site conditions may impact the counts we're getting. And it also doesn't take into consideration any of the spatial patterns that may be at play in our survey. So for example, on my site, there are large areas that are made up of dense coniferous forest, and there are other areas that are completely devoid of forest. And it's not unlikely that our ability to see moose in these dense coniferous forests is going to be much less than our ability to see these same animals if they were found in this non-forested area. So we have to account for this to improve the accuracy of our estimates. So how do we do this? We do this by using a model called a density surface model, which is a specialized type of generalized additive model. And in this model, we're using the detection curve from our first analysis, from our first model, as an offset to correct the survey counts now in our new model. And additionally, we're comparing our variables of interest to this corrected count data in a fashion similar to a generalized linear model. Except in the generalized additive model, we can not only analyze linear and continuous effect, and we're able to look at continuous and categorical effects, but also nonlinear relationships that may be occurring in the model. And this is done, these nonlinear relationships are looked at by using a penalization formula, where if something is important, it will penalize the model accordingly to correct for this issue of nonlinearity in the underlying data. So in this package, we use the function DSM, and the formula is the variables we're testing based on count data. If we're looking at the abundance, and if we wanted to look at the density instead, we would choose density equals these variables. The DDF dot object is our detection curve, which DDF is the name for the part of the density, the distance sampling model we did prior. The segment data covers the information about our variables of interest. The observation data covers the information about our group that we're observing. The transect variable does the exact same thing as it did in the distance sampling model. Same thing with convert units. And finally, if we wanted to use a set distance away from the line instead of a distance determined by our detection curve, we could specify that distance by using the strip width. And we have the ability to define what family our model is going to be it quasi-Poisson, Poisson, negative binomial, Tweedy, or Gaussian. And for those who are not familiar with what a Tweedy model looks like, it's very similar to a Poisson model in how the data kind of shapes out. So this is what my segment data looks like. I have my lines from the first analysis, and I have decided to further subset these lines into line segments to improve the accuracy of the variables of interest. So instead of going for my line being 4 kilometers long, I have it now broken up by 1 kilometer sections, or in this case, 885 meter sections. And I'm giving the location of a centroid for each of these sections, as well as the forest type in each of these line segments. Here, I'm showing the observation data, which includes the line segment number, the object ID, the size of the group, and the distance that group was seen from the line. So I'm just showing this picture to show how much the points are clustered in certain areas of the site, where we have most of our groups in the northeast, or sorry, the northwest of our study area. So to account for that, we're going to treat the location of these groups as a non-linear effect, because clearly there's just clustering rather than some kind of gradient on the landscape. So in this, I decided to use a simple spline with the X and Y variable. The other option is to use a tensor spline, where you look at the interaction between the two variables in the non-linear variable. And in this model, instead of giving us an estimate for the effect of this non-linear model, we're instead given a penalization number. And generally, if the penalization number is below 3, we assume that the model doesn't really require this nonlinear effect to be put in. And if it's a lot more than 3, that gives more evidence that the penalization is both necessary and significant. The other thing to point out is that our original model detection curve is this variable right here, and that we're using a quasi-Poisson family for this model. And because we're using a form of a Poisson model, we need to not only look at the estimates, but rather we need to look at the unlogged odds ratios for this model to really look at the impact. And we see that across the board, moose are preferring forested habitats compared to non-forested habitats, but the mixed forest is not significantly different than what we would expect given a 95% confidence interval. So the density service model tells us how our variables are affecting our count data, but it doesn't really tell us how the abundance is impacted by these variables. To get that information, we have to take an extra step and create a predictive data set based on our study area. And I did this through the creation of a shapefile in a JS package and then bringing it into R using RDAO. So in each of these squares, I determined the location for the centroid as well as the habitat type at the center of each of these little squares. And this is a grid of 7,300 squares, each square being about 1 kilometer in size, with some squares being smaller than 1 kilometer due to this whole shape not being a perfect square. So this is what my predictive data grid looks like. I have my X and Y for each of the squares, the habitat type of the square, the area of the square, as well as the region the square was found in. Now, unfortunately, the DSM model can't really read this table directly. So we have to first turn it into a matrix using the split function. And once that's done, we can then use the function dsm.var.gam, our original DSM model, the predictive matrix we just created, and an offset based on the area of our original predictive data set to come up with a population estimate. So that's what this looks like when you look at it with my own data. So we have our original DSM model, our predictive matrix we just created, as well as an offset based on the area in our original predictive data set. And that gives us an estimate, a standard error, a detection coefficient of variance, a model coefficient of variance, and a total coefficient of variance. Now, again, to get out all the information you would get from the distance sampling package, you have to take a slightly extra step by separating out each of your regions using a subset function before you make a matrix out of your predictive data. So when that's all said and done, we're able to graph the location of individuals on a landscape based on our model. And I did this using ggplot and map tools and dplyr to combine my original shapefile with the new data I got from this analysis. And after testing other mapping softwares today, I would say that MapView is actually probably a better tool than map tools to do this kind of work, but that was what was used in the original example, so I decided to keep it. So finally, when we compare the two methods to one another, we find that the 95% confidence intervals for the two estimates are almost identical, but the DSM package results have a lower coefficient of variance, so they're more accurate. And that was our goal for doing this kind of work. So I'd like to finally discuss the advantages of the density service model package over the distance sampling package. So it's more accurate. It allows you to account for additional fixed effects. It works well with spatial R packages, and it's much more versatile when it when it comes to trying to analyze this type of data than the distance sampling package. However, the distance sampling package is much easier to use. The output it gives for its calculations are a lot easier to interpret, and the steps required to use this package are a lot fewer. The other thing that the distance sampling package can do that the DSM package cannot is that the distance sampling package can account for variation in the detection curve. So one of the things that I tested was looking at how group size impacted the ability to see groups from the line. And I found that there was a significant relationship between group size and detectability of that group. However, you can't really use this information in the density service model because of how it's set up, where the main focus of the distance sampling package is the detection curve, and the main focus of the density service model is the count data. However, even at this point, when you do correct for the distance sampling changes in the detection curve, it didn't explain as much variation as all the other options that are available for the density service model. So I'd like to finally talk about the fact that both these packages are made by the same group of people, and that this group of people has a website. And if you're interested in doing this type of work, I would highly suggest going on their website, which is distancesampling.org. And on this website, they have free tutorials as well as monthly workshops they put on that are also free. And if you're interested in this type of work, I would highly suggest looking at their website. And if you have any questions about this package, it's probably best to contact the people who made it. However, if you want to contact me, here's my contact information. The top email being my personal email, and the bottom one being my professional email. And I'd like to thank you all for listening to me talk. And I think we have about 7 minutes for questions.
Nice. Thanks for your talk. It was really, really well broken down. So we have a question from Denise. She asks, can this be used with multiple species, or is it designed only for single species?
So it can be used for multiple species. The only issue I would say is that the distance package allows you to really look to see if two different species have a different detection curve. That doesn't really, or that is a lot hard to do in the DSM package. You can still use the two species as a fixed effect. It's just that the way the DSM package is set up, all the variables of interest have to occur in all observations. So you can't have an observation number that follows multiple different sections. That's why you can't look at group size in different groups, because you're only going to get a measure for each of those groups, and that will be different for each line segment. So you can do it. It's just that there's a little complications to try to do it.
Okay, we have another question from Kath, and she says, I'm wondering what types of animals is this best suited for? I assume it depends on the sampling methods used. Is it highly mobile animals observed from a distance or line only, or would there be other applications in animal types?
Yeah, so this model was originally designed for use on whales, and this type of analysis can be used just as easily for point surveys. The only thing, I'm using it for transects because that's how you track moose in this case. I would say that distance sampling is best for animals that are dispersed across a landscape and that are not highly grouped. For animals that are highly grouped, it's suggested you should instead use survey methods or census methods and then do subsets of that population if they're all in the same location. This type of survey works best when you have species that are, again, dispersed. So for example, I use distance sampling for moose, for white-tailed deer, but I use censuses for elk, for bison, and for Barron's caribou. And when it comes to forest living caribou, you can go either way depending on what time of year you're doing the survey at.
Okay, we have a question from Rui who asks, is it possible to use on random surveys?
Yeah, so I have used this survey method to improve the accuracy of gas-away surveys, which are basically you survey an entire area quickly to determine a baseline of what is a high, medium, and low area. And then you go back and you secondarily survey a subset of these areas to determine what is the average high, medium, and low density area for a population. And when I do that, instead of using a detection curve, I use the bin width, not the bin width, the something width. One second, let me just look for the terminology. And when I do that, let's see, I use the strip width to define the area the survey took place in. That way I'm only looking at a given area for the survey rather than a detection curve for it.
Okay, we have a question from someone on the YouTube feed from Pamela, who says, you mentioned that the effort equals length of line. So if I walk transect A, which has a length of 1,000 meters, a total of 8 times, and I only see animals on 2 walks, how do I include those extra 2 walks in the data?
So the way this kind of survey is set up is you would not walk a line more than once. But if you did do that, then you would turn this into a mixed model. And in the mixed model, you'd basically put each of your lines in, and you would basically decide on a random effect to represent the series of your walk. So maybe the day you're doing it on, or the time of year, or some kind of measure to account for how this whole thing plays out in time. And that's how you can control for the variation between your different observation periods.
We have someone that, it's not really a question, it's more of an interesting comment. They said this would be interesting for trapping mosquitoes. But I think that brings up kind of a good question. What is the possibility of reducing the spatial resolution so much that you could perhaps do something for like insects? Is that possible?
I mean, yeah, technically speaking, I know people who do this with protozoa. Like all you have to do is basically,
Oh, wow.
the question becomes like, is it harder to see protozoa on the edge of a microscope slide than it is in the center of the microscope slide? And same thing with mosquitoes. If you could see mosquitoes, or if you could measure mosquito numbers at various distances, the question becomes, is there some kind of difference in this resolution on that? And if there isn't, then you might not want to use a detection curve. You might just want to use a survey area rather than the detection curve part of the DSM.
Yeah, that makes sense. We have another question from Ala, who asks, is it possible to handle data with spatial autocorrelated in distance sampling?
Yes.
Yeah.
So yes, I haven't gone too deep into what you can do with the nonlinear data sets, but I would say there's a fair amount of robustness in the generalized additive model when it comes to dealing with a lot of different nonlinear relationships, including spatial autocorrelation. It's just that one of the things that's against generalized additive models is that you can over parameterize them, and they start to lose perspective because you're putting in so much information and you're no longer really seeing a real world application anymore. You're getting like the perfect answer, which is a problem sometimes in data collection.
Any more questions before we move on? I'm watching both.
Someone makes a comment that they use this on geese, and that's true. And I've also used it on whales, and I've used it for sound, like for whales. I've used it before. So you can do a lot of weird stuff with this. Like it's not just observation. It could also just be other detection reasons why you wouldn't be able to always detect an animal.
Okay, I think that might be it. Are you good?
I'm good. Thank you.
Okay. Well, thank you for the talk. That was again really well broken down. I appreciate how you went through each of the functions, all of the arguments in them. So if anybody was trying to reproduce this for their own work, I truly believe that this would definitely help them in doing that. So we will move on to our next speaker. So Emy Guilbault, who is from University of Newcastle in Australia. I'll leave it to you, Emy. Having a bit of trouble hearing you. I think it might be your microphone volume. One second, Emy. Could you try unplugging and plugging back in your microphone? I can't hear it at all. No, I still can't hear, sorry.
If I work without my headphones, is it better?
Slightly better, but still very low volume. I think it might be the microphone volume controls on your computer.
Is it better or it's still not?
It's still very low.
I'm not sure, because the problem is I had the issue with my computer crashed and I'm not using my computer right now. So. Is it better now?
No, so if you type in microphone to your search, then you should be able to access the settings. Yeah, just turn that volume way up.
Okay, what about now?
Oh, no, that's the speed. So on, where is, there should be a volume bar somewhere. Let me check it on my end. Microphone setup. Yeah, I'm not sure why. So maybe on Zoom, if you can go to audio settings and then try turning up the microphone volume on the audio settings in Zoom itself.
What about now?
Yeah, under settings, you can change the input volume for the microphone.
Did you find it?
Yes. But it was always really too long, so I can see your plans.
Yeah, so try turning it up for the input and output.
Yeah.
It's a little bit better.
Okay. Do you think it's going to look like that or?
I don't know. I mean, if that's what you can work with now, then it's okay. We can try to follow along, but you might have to speak really close to your microphone.
Yeah, yeah. I'll try that. The thing is, it's not by computer.
Oh yeah, that's much better. It's all right. Technical difficulties like these are to be expected at this point.
Yeah, the problem is my computer crashed exactly this morning, so I'm using another one. Someone else.
Yeah, no worries. You got time.
Okay, well, then let's start. I'm going to show them my screen. So, can everyone see my screen now?
Someone says you might have the computer microphone chosen instead of the plugin or the earphones. I don't know what they mean by that.
But you said it's better now, right?
It was, but as you go even a little bit further away, we can't hear you at all.
Okay, so I'm going to speak very close like that.
Yep, that works fine.
Okay. Well, good morning, everyone, and I wanted to talk today about simulation of ecological datasets using main focus for this story. But
Hey, Emmy.
yes.
Sorry, somebody suggested you could try joining Zoom with the phone, and then I'll add you as a co-host with that because it's like we cannot understand anything that you're saying, unfortunately.
But with my phone, I won't be able to share this. I will be talking through the phone.
Sorry, what?
So I will be talking through the phone and showing.
Can you type it? I honestly can't hear anything that you're saying. Again, take your time. We're not on any schedule here, so no stress.
Okay. Can you hear me?
Yep. It's echoing. Oh, okay, it stopped.
Yep.
Wait, no. Now it's echoing. Mute the computer. Yeah,
You also have to turn off your sound on your computer, or it'll echo.
Yeah.
say something.
Is it better now?
Oh, it's perfect.
Great.
All right.
Okay, let me start all over again. So you should see my screen now, right?
Yep, can see and hear you perfectly fine.
Well, then let's start. So I wanted to create this talk first because I've been working with species distribution modeling, and I've been using a lot of ecological datasets. And the idea was to be able to have practical simulation of species that can allow you to play with the data and be able to test better the different models that I've developed during my thesis. So first, I will introduce what data I'm talking about and what species distribution modeling are. And I will include some aspect of citizen science because that was the main focus for the project I was working on during my thesis. And then I will develop on how to simulate some changes in the environmental covariates and different aspects about the data observation. So how we do some recording in space and what kind of variation there is, as well as the observer recording and how that can also change. And I will finish by talking about data dynamic, how through years we can also have changes in the way we observe data. So first, let's focus on species distribution modeling. In species distribution modeling, we usually have observations that can come from various sources and through interesting environmental covariates, I don't know, altitude, temperature, you can predict where the species is more likely to be. And it's important for conservation aspect or any kind of survey. I assume that many of you have seen or heard of species distribution modeling before. The thing is, those kind of prediction can be as accurate as what you input in the model, the observation first and the environmental covariates too. So depending on the type of data you will consider, presence only, occupancy data, presence absence, abundance, you may not have the same quality of data per se. If you have some observations that are from opportunistic survey, like presence-only data, from citizen science data, anyone can make a recording, and those kind of recordings can be not very precise in terms of location, in terms of species. There can be some bias or misclassification, those sorts of variation. If you have occupancy data or presence absence data, we already think that those can be a higher quality data because you've set some sort of survey space and you visit those places. For occupancy data, you will visit multiple times the places. And the idea is, even if you have high quality data or low quality data, all of them can have variation, and in terms of how the observer makes the observations, and also how easy it is to make the observation. And what we need to think about is, no matter what the true intensity is, which is explained by the suitability of a species in its environment, depending on any kind of bias, what you will observe will be different from what's the truth. And in our model, we usually test if our model are accurate according to a true pattern or true intensity that we try to verify. So what I want to be able is to test different various cases of degradation of the data that we observe and see how we can create better simulation for that. So during my thesis, as part of one project, I was looking into data quality that I've kind of divide in different aspects. There is first the observation accuracy, where we have some misidentification, where you have either the species that is not the one you should have observed, or you can also have the observer trust. Your observer can be a specialist of a species, a very, very well experienced person, or maybe a random observer that is just adding some more information to a data set. You can have aspect of data sampling, where the observer behavior following road network can very well influence the observation. And you also have some aspect of spatial coverage. Maybe some ecological barrier could happen, a pond, a mountain where a person cannot go and do the observation. So the pattern of observation that you will see will also be degraded. You also have some variability in time. From 1 year to another, some point can move due to movement in general, going to a different place, or birth or death of points. You also have some maybe uneven recording over time, so you may observe less points from 1 year to another. And again, according to the different type of data, the different protocols, we have various input data to access for models. So the idea that I wanted to present today is some tools that I've developed during my PhD to sample and simulate data and to be able to account for various of those aspects. And I've definitely used them in my simulation to be able to test my models and see how they can account for better or worse data, and how they can more accurately predict species distribution. So if I first start talking about environmental layers, because I said that's one also of the aspect that can be changing, and the quality of it can also be of various aspects. I'm going to present to you how or with what tools we can look at those changing environmental covariates. So here I'm just displaying the different packages I've used. I've also used some functions that my supervisor, Ian Rayner, developed for another project. One thing I want to focus on also is I need to define a quadrature grid. Here it's just on a space of 100 on 100, and the idea is to have this grid of points where you can have the environmental information at each of the quadrature points. We also define a certain window, slightly larger than the grid. And I wanted to talk about the NLMR package. So that's the package here that I've loaded. This package is really good to show some real type of ecological environmental covariates. It's based on some different processes like fractional Brownian motion, Gaussian field, etc. Those processes are usually used to study hydrology, altitude, and rainfall. So I found them very useful to simulate something that's from the truth. You have different parameters in those functions that allows you to do various simulation to play on the smoothness of your pictures here, and to simulate here, you see how precise or pixelized can be those environmental covariates. Now, this is not my work, but I've used those created environmental covariates to simulate some changes. And the idea I first thought about is that changes can come from center of disturbance. So I decided to create here a point of disturbance, which are a bit exaggerated here, 30 just to show you, but you can create obviously less. And I transfer them to spatial points, which allows me to calculate distance from anywhere in the window of these covariates to the center of disturbance. And then I can degrade these covariates through the years. I decided to degrade it using this distance. First, from a germ time to year 2, we can just degrade with the distance, which create here, you see those little center of black, which means that we degrade the environmental covariates and we don't have a high intensity for this particular information. And this third year, I decided to degrade even more, 10 times the distance, and you see I've increased those center of disturbance. So it allows you to see some changes and degradation of these environmental covariates. What can be done also is not only this central disturbance through points, but also through distance. Distance meaning just on an axis. So I've been working on also another type of disturbance. Here we create general covariates with X and Y. So it's just to define these covariates. And I decided in the second year to change the value here for the y-axis, which will look something like that. You see that I've pushed on the side this intensity of the covariates. What's important here to see that the information that we will have at our quadrature point will change because we change one of the covariates. And where we're going to sample points from this first covariate information to the second one will obviously be different. If the intensity is high for the red color, you see more points here, and with blue going more on the right, sorry, for the second year, those points will also change. So I wanted to have different aspects of disturbance here. You could think that maybe there is some human intensity that could be increasing or some sort of disturbance like that. Now, how do we get from this vision of environmental covariates to sampling points? Well, that's the notion I'm going to develop on this second part. How do we record points for landscape and its change? So to generate presence only data, so points, those points location in space, we usually consider some coefficient here that will show how the species will be interested in every covariate, how it's going to like it, and you model the intensity as a linear function of the environmental covariates with the coefficients. This intensity is presented just below on the first map here, and you can basically sample points using some function from Spatial for creating your Poisson point process with this function. And it displays the plot on the right here. But this is not a direct sampling like I want. It's just a random creation of point according to a Poisson process. Now, if we want to do a sampling, I need to get the information at the quadrature points. So in the background of my environment, I have defined then a data frame with the different environmental covariates I've talked to you about before. And I need to define my species the information of these covariates at the species point. So with this function that has been one of the functions that I talked about that have been loaded from previous work from my supervisor, I've been using that to get the information here at the species location. And through that, you can focus on your point pattern and define with a coefficient, with the information at your species point, a new intensity, which would be the sampling intensity. The change here is mainly to work with a different intercept will allow you to have a higher or lower value intensity and have a different number of species that you can sample. And we will do this sampling using the sample function. You can choose obviously the number of points, and it can be according to the intensity that we have created for the point pattern here. Now, anyone could do those different steps because it's used already existing functions. But what I wanted to talk about is how can we do a better job here in sampling. So I've created a function that is that allows us to sample the points directly. And let me give you an example with an extra variable, because in here I just presented how to normally sample, but we can sample with degraded points. So instead of having only my 4 covariates, I had a distance to the road covariate. So I've created a road network and calculate the distance to the road, thinking that a person will more likely follow the road to observe a species. And this is my new environmental covariates. I have still my coefficients. And with my function SimPeo, I just input those information. The intercept that I want, if I want to change it compared to the coefficient I had, the number of points I want to sample, and you can have these kind of plots. So this is just a function that allows you to sample information. Those different parameters are just about if you actually want to do a sample or if you want to keep going with a true intensity. You also have a way to display or not the plot, or just having the output, and to have comparative plot like what I showed you here. So this is an example with a road network. You can also do a similar work with vegetation or habitat facilitation. You can think that if we create here a new environmental covariates, I've changed it to be categorical to show that maybe in the blue area, in the red area, we have different facility to observe a species. It would be less likely in some colored area. And we integrate this variable to our environmental matrix here. We still have our coefficient, and we input again that into the SimPeo function. And you see that you have again a change point pattern here according to this new covariate too. And this is something I also wanted to develop for occupancy data, because obviously occupancy data, even if it's a higher quality data, we also want to be able to account for some of the data quality issue we can have. So in occupancy data, the idea is you've divided your grid of observation into some quadrant here, and what we want is to visit each of them. And when you visit each of them, you either don't see a species, so that's the white, or you see a species, which is the purple. And you do that for a certain number of visits. Here I have 5 visits, and you sum all those visits to get the history of the occupancy sites. And you see some sites have been observed, have a detection of a species 5 times, and some other will have no detection of a species. Now, how can you have a function that allows you to simulate those? Well, I'm basically using some codes that have been developed by my supervisor here to create this function. And this function allows you to play with different parameters. Again, you have a coefficient, your environmental covariates. You can play with the distance from the center of your visit site to the area you want to look for any detection of species. So here 0.2. So in an area 0.2 around the center, did I find any species or not? You can choose which variable would be of interest for your priority of detection, and choose the number of visits and display the occupancy plot. And that's the kind of plot you can get. And we'll see in a minute that we can also change this occupancy plot according to all the type of covariates and all the type of varying aspect of data quality. For example, if I want to consider spatial coverage, which was another aspect I've mentioned before, I created here covariates where I have this extreme area that is an ecological barrier. Let's say it's an area we can't access at all. So that's why I have this area that is in dark here. That's still my true species intensity, but you see that this area is not accessible. We don't have any information. I just have to add these covariates to the rest of my environmental covariates, input it in my SimPair function, and I get a degraded sample point pattern here where this area is not doesn't present any data point. And I can use that also for my SimOc function, so the function I use to simulate occupancy data. The idea is here, this area where we don't observe is not only part of the environment, but it's also changing your probability of detection, because obviously you cannot detect in this area. So here I had to modify my previous probability of detection. I previously used a certain covariate, so I need to have a new covariate where not only have this environment where I have a certain detection, but I also have an area where I can't have any detection. And similarly to what I previously shown, you can have simulated occupancy data history like this, where in white here you have no detection at all. Now, this is just about the environment, but something that is sometimes a bit overlooked is also the observer accuracy in its recording. So let's have a look on how we can simulate those kind of information. You could first think about misidentification with false negative observation. Basically, it will be having a species, a point location that we consider not being of species of interest, but from another one. So I wanted to be able to sample that. The idea is basically always using this sample function with a certain number of points that you choose, and you can make it about the species intensity. We could also make it from a random perspective, but here I didn't show it. And I created a function that integrates this part and also the sampling part I've been showing you before. So this function with similar parameters at first here, and then choosing if you want to do the misidentification, what percentage of points need to be misidentified in your point pattern, and you can then change and create how many points you simulate misidentified, or and how they are misidentified. Misidentification can also be with false positive. So the idea for false positive I was thinking about, you can have other species points coming from a species that have similar habitat preferences, and unfortunately someone who maybe not experiment or can't differentiate the species may record them as the species of interest. So I created a function called multiple PO, where you can create basically multiple point process pattern. And the idea is here I have coefficients from species which are somehow similar habitat preferences, and I can, with this function and list of arguments, choose how I'm going to sample those species, number of points, etc. And you can create multiple species like this and have an output, a point pattern that shows a misidentified with false positive points. And finally, I would like to mention how points can be dynamic in time, because usually when you observe or when you use a point, a type of data sets, point patterns, you have a time constraint picture, but it's not exactly what's happening. And you have to have a dynamic idea if you have a data set for a year and be able to simulate such changes. So I've worked on different aspects of simulating depth of points. If we have our point pattern here, we have a certain probability of depth. You can again use this sample distribution to choose which point are going to be considered as dead. The idea here, I'm using a random process to make those points chosen. You can obviously vary the probability of death, the standard deviation here, and some information. And we see here that those points are randomly chosen. And I've decided to generalize this function to be able to have not only a random process, but also some habitat suitability process, because you will think that in less suitable environments, some points are more likely to die than in other environments. So I created this function called depthPoints, for which you can input the result from the SimPAO function I was talking about just before, choose your probability of death, choose this value of standard deviation, and if you want a random depth process, or if you want to account for the habitat suitability. And you can see you can vary how this depth process can happen, how many points are considered, etc., etc. Another important aspect would be birth and colonization. The idea is here, how do we create points? So I have this function that I've created called birth points, and I decided to work out two different aspects on how we create points. First, the birth process here that is simulated in this function work as we choose some parent points, and we create a buffer around those parent points where offspring's points can be born. Obviously, they cannot be born everywhere. We choose the radius around the points. We can choose also what percentage of offspring points are going to be born, and or not all points are going to give offsprings. The idea is here, it depends on also the habitat suitability. So our presence only intensity that we always have in the sample function since the beginning. For the colonization process here, the idea is just have points that kind of arrive in space here according to also the habitat suitability, and there's nothing other directing this income of points. It's just about those points creating its space according to the species preferences. But you can also choose how many points are created with this, this parameter. And finally, I wanted also to have a sense of how points can move in space from one year to another, from one time to another time. So I have this function that I've created, move points, that also input again the result from the SimPAO function. And I have different ways that the points can move. First, it can be a random movement. You can choose to move all points if you choose all points equal true or all points equal false. So the two plots here are basically showing you the second case. I decide not to have all points moving, but rather I choose with p move a proportion of points in my point pattern that are going to move. We don't have to focus too much on those two parameters yet. And you can again play with some mean and standard deviation in how your random sampling is going to be done. I haven't played that much with them in this talk, but it's something that can be done. The second way we can have movement in space, it could be according to the habitat suitability. You'll think that in more stable habitat, some point will come closer there. So you can choose again, have all points moving or not all points moving as shown below. You can play with some of the parameters here. and you have to choose the move type as intensity. You again choose how many are moving if it's not all, and that's about it. Obviously, if some points are moving too far, they may go outside of the window and they will be erased because they are not in our focus space here. And the last way we could have a movement, it would be according to habitat suitability, but habitat suitability meaning focusing on one particular variable. So with the same input, I choose this time the move type center, meaning that the points are going to move towards the center of a particular covariates, the center of high intensity. You can again move all the points, and that's what I've decided to show you here. You choose which variable is going to be the one that we focus our points movement on. And you can choose the scaling, meaning how are we going to scale the coordinates of the points toward the center. So here I choose with the value of 0.2, and you see that those red points here move toward the center. And we have a change here. Obviously, it's a bit an extreme change. If we have a look at not all points moving, we have something like this, where the dark blue points become the new light blue points. And I've chosen exactly the same parameters, but this time I have not all points chosen, and I've decided how many or what proportion of them are going to move. So I know this might seem just about practical function, how you can use them, but I found them quite useful to have an idea of what's happening to my points and how such covariates, some covariates and the change of covariates can influence the sampling and how my data are going to be degraded if it's a bias covariates. And I've intended here to have functions to make it easier and more applicable for myself and everyone who see. And some of them may soon become our package, why not? But obviously, it's still a work in progress, but I wanted to show it. So I'm happy to have a discussion with it now.
Wow, thank you for that talk. I think there's a lot of questions about species distribution modeling in general in the ecology and R group, at least like 2 every other day. I have one question about one of your slides where you mentioned that there may be some geographic barrier where you don't have the observed points. And it looked like you added that in as a roster into your covariates. So does this work the same way as a bias mask? So if you're putting like a kernel density mask around your points so that you prevent your predictions from going outside of that area?
So how it works for this one, the idea is I have this covariates which is categorical. Actually, I don't show the covariates, but the idea is this part of the covariates would have a value of 0 and the other one of 1, for example. And I've put a really high coefficient to mean that the sampling and how it's going to be sampled according to this covariate would be very far off this area. So if you have a smaller value here, you may have a couple of points coming up in here. So it's not exactly a mask because you could have points with a smaller coefficient.
Okay, so basically you're just telling the parameter that this is very unlikely to be the most suitable.
Yes.
Okay. We have a question from Laura who asks, could you explain how you get the habitat suitability values?
Yep. So for the habitat suitability, the idea it's more about, I consider the habitat suitability looking at a species intensity. So you have, maybe it's easier this way, you have some coefficients which represent how the species is going to like or not a particular environment. covariates. So I have 4 covariates at first, V1, V2, V3, V4. That's just my intercept. And if you have a 0.6 or -1, you see that you are positively attracted to the center of these covariates, of a space of high intensity of these covariates, with a negative value here, you will be not attracted by the center of this high value. So the species intensity is a combination of your species preferences and environmental covariates as expressed with this function. It's the same idea when you express the intensity of presence of your species by a log, sorry, I lost my words. It's basically based on the intensity that we work on with Poisson point processes, where you explain the intensity as a log linear combination of environmental covariates.
Great, and just to build on that point, you had a section about movement and habitat suitability. So you said that you choose a particular habitat that the species may be moving towards, and how would you choose that specific variable? Do you go by variable importance or by expert opinion on the natural history of the species?
I think here, yeah, it would be for the person to choose according to what they think would be one of importance. It's really a simulation work, so you will be the one choosing which covariate you want to see the points attracted toward the center.
Okay, perfect. Any other questions? We have, I'm monitoring both the feed from YouTube and from here in Zoom. So if you guys ask here or there, I'll go ahead and ask her for you. Give everybody some time to think. It's a lot to take in, I'm sure. Okay, we have one here from Alfredo. There's a point I'd like to clarify first. For now, it's all based on simulating the environment and space and everything else, right? So if that's the case, I think there are really cool things you can do by using empirical environmental data, virtual species generation, and integrating the functions to evaluate the possible sampling bias by your observer on a virtual species. So you have a real environment, but you have full knowledge of where the species will be, but not on where the species can or will be sampled.
From what I understand from the question or the comment here, yes, it's all simulated work, but indeed you have the possibility to maybe input real environmental covariates and maybe have a go on simulation and see how, if I come back to the right, how am I going to sample presence only data, how the points could change in space according to these environmental covariates, add some observer bias. Definitely that's all possible. Yeah.
Okay, and we have one from somebody on YouTube who asks, if I have a variable from the field, for example, water depth in meters, and another variable is a patch area in meters squared from Sentinel-2, can I use these variables to model species distribution?
Can you repeat the type of data exactly, please?
So I think they're talking about marine or aquatic species. So they say their one variable from the field is water depth and another is a patch area from Landsat data.
Yeah, I will definitely think that those can be used, but as usual for species distribution modeling, it's important to know the type of data you input. So the resolution of those environmental covariates, how precise they are, but it also depends on the type of work you want to do. I think it's feasible, but it has to be carefully done.
I see on your current slide you have road network data. So one of the issues that I've ran into while running species distribution modeling, especially with Maxent, is that when you use these anthropogenic layers like road data or human footprint data or something as a raster covariate, oftentimes when you're using your citizen science data, especially because everybody is close to these, that becomes your highest predictor for variable importance, or for like, it gives the most power to this. So how do you mitigate that?
I think one thing you could play in the simulation here, it's playing with this coefficient. So this last coefficient corresponds to my distance to the road one. That could help because obviously here I have something that seems to be quite triggered by those road network. I would think that also while creating the road network, it depends of the intensity. The one that I've created here is simulated and it's not very smooth. So I guess playing on the smoothness when it's simulated, it's also going to help, but it's definitely not something you can have while using a real data set with road network.
We have another question from Allah on YouTube asking, can we consider the biotic factors while creating our simulated species range?
What kind of biotic factors do they, did they mention any?
No, let me ask. I think you covered quite a few on the birth and death and movement. I would consider those to be important biotic factors, but we'll see what he says.
Mm-hmm.
In the meantime, anybody here on Zoom have any more questions? Oh, also, did you give the code and package link in?
So it's not yet a package because the function I've created them quite recently. At first, it was just my own code and stuff, working on those different type of changes. The function are now almost ready, but I have a tutorial that I can give a link to. Yeah.
Cool. Okay, so Allah has said that he means like interaction with other species, like predation.
Yeah, so that's a really good one. It's not included yet, but I've definitely think about that, how the interaction with another species would work. So I'm guessing that's a work in progress, and that could definitely be included in the type of simulation, especially with the function multiple PO that I've presented before, where you can even if it's this one was in the case of misidentification, it definitely creates multiple species. So something I could include is a way to work out interaction with species. So allowing points to be either closer if they're attracted to another species or repulse to some other species. Yeah.
Yeah, and building on that point, I think it would also be interesting. I see a lot of community ecology papers now using indicator species as one of the metrics in their communities. And a lot of the time, these are on pretty small spatial scales where they're doing a trapping study or just survey transects in a portion of a national park. And I think it would be interesting to be able to simulate whether or not those species are in fact indicator species, or if they're only indicator species in a certain habitat type or certain environment, and maybe see like the percentage overlap when you predict their distribution.
Yeah, that's actually a really good idea. Yes, definitely. But like any functions, I mean, those are some aspects I've thought about looking at, and there are so many other possibilities. That's the good thing about simulation. You can kind of create your own possibilities.
Absolutely. Any other questions? Okay, well, I think that's it. If you're fine with the questions so far, is there anything else that you wanted to explain? Letting go. You want to? Did you already give your information if anybody wants to contact you about your talk?
Yeah, I think I had my email address at the end, but I can add it in the chat just in case, and I can maybe, I will probably write on the Facebook group a link to the tutorial and my GitHub space, those kind of things, I think.
Perfect. All right, everybody. So that will conclude our talks for today. We have another set of talks on some statistical concepts only in a few hours. So that's going to be in 4 o'clock p.m. My time, or rather 4 o'clock p.m. China time. So that's GMT +8. So we will see you for the next set of talks. I will also post the link to the music, and Emy will post the link to her GitHub pages and everything on Facebook. This talk is going to be recorded and available on YouTube, so anybody who wasn't able to view it live will be able to see it later. Okay, see you later, everybody. Take care. Thank you for the speakers, and thank you for everybody that came out to view the talks.